actually my first time at ICTS, so having a great time. And yeah, this talk is going to have, in many ways, a lot of overlap with what Peter talked about, even talking about some of the same papers. It will be a theorist perspective rather than an experimentalist perspective, so hopefully it will be synergistic rather than duplicative. And yeah, this is some of the papers that I'll be talking about in this talk. Now, so let me start by motivating this, and in some sense, maybe it's not even necessary because Peter gave such a fantastic introduction to the topic. And yes, nonlinear spectroscopy provides a wonderful new set of tools with which we can interrogate material systems. But I'd like to offer a different and deeply personal motivation for this. So, over the past decade, now more than a decade, I've pretty much been all in on non-equilibrium quantum dynamics. And when I want to be provocative, then I start my talks by saying that the 20th century was a century of equilibrium condensed matter, and the 21st century is going to be the century of non-equilibrium. No. I would like to believe that this is true, if only because I've gone all in on non-equilibrium. And certainly there have been a lot of developments in non-equilibrium sort of condensed matter theory over the past decade. But at the same time, if I take a sort of hard-eyed look at it, I would have to say that most of the realizations of those ideas have been in synthetic systems. Yeah? Whether it's cold atoms or trapped ions or quantum devices, it's almost always synthetic quantum matter. Now, hey, there's nothing wrong with synthetic quantum matter, but wouldn't it be nice if there was interesting non-equilibrium many-body physics to be done in the truly materials or solid state setting? Yeah? And the usual objection there is that, well, if you're talking sort of solid state or materials, then you have phonons, for better or for worse, and phonons function as a reservoir, and they lead to the system thermalizing once you wait long enough. Yeah? So the sort of long-time steady-state behavior of solid-state systems, material systems, generically is just governed by equilibrium condensed matter. Okay, I mean, this is a valid objection. At the same time, phonons don't thermalize things instantaneously. There's some time scale on which phonons and electrons couple and lead to the system thermalizing. And so you could just say, hey, let's look on timescales which are short compared to the timescales on which phonons make everything boring. And I'll define boring as anything that's not out of equilibrium. So let's look at timescales that are short compared to the timescales in which things go back to equilibrium. And then maybe we have something interesting to play with. Okay. The only challenge is that the typical timescales on which phonons lead to equilibration are maybe picoseconds. So you need to be looking on timescales which are short compared to picoseconds, which means you need to be sort of working on ultra-fast timescales. Okay? So that's maybe one motivation for ultra-fast interrogation of materials, which is quite different from, well, of course, it's absolutely true that ultra-fast interrogation of materials allows us to read out information that's inaccessible to conventional techniques, and Peter gave us many wonderful examples, but also from a conceptual point of view, it's nice because it allows us to do interesting non-equilibrium many-body physics in material systems instead of synthetic systems. Okay, so one motivation is just to apply ideas from quantum dynamics to gain insight into material systems. The way I'll structure the talk is as follows. I'll begin by briefly reviewing two-dimensional coherent spectroscopy. This will be pretty fast because Peter already presented 2DCS and the application to silicon. Then I'll introduce the idea, I'll talk more about nonlinear spectroscopy for spin liquids and fracton phases, nonlinear spectroscopy for superconductors, and then some outlook. Yeah? So the talk really will be structured as a bit of a survey. It's the last talk of the day. Probably you don't have the energy for a really deep dive into one topic, but I'll try and leave you with a sense of the sorts of things that nonlinear spectroscopy can do and where it might be headed. Okay, so start with another review of 2D coherent spectroscopy. So new experimental technique, well, not all that new. In fact, it was first introduced 50 years ago in the context of NMR systems, and then very widely applied in physical chemistry. Where it is new is in application to material systems, particularly in the sort of terahertz regime, where interesting many-body physics might play out. Now, what problem does 2D coherent spectroscopy solve? Now, what I would say is that the fundamental problem that we know how to solve with 2D coherent spectroscopy is the following. Suppose you have a system where there exist sharp excitations, but those sharp excitations are not visible to linear response probes. Yeah? Whether it's because of inhomogeneous broadening or because those sharp excitations are part of some many-body continuum. So in linear response, you just see some broad fuzzy thing. Then you can use multidimensional coherent spectroscopy to resolve the sharp excitations which underlie the multi-particle continuum or which are being messed up by inhomogeneous broadening. Yeah? And I'll give you many examples of how you can do this. Basic experiment is essentially you shine 2 pump pulses and then you probe. So pump once, wait a time t1, pump again, wait a time t2, and then probe. So now you get a nonlinear response, which is a function of 2 timescales. There's the wait time between the 2 pumps, and then there's the wait time between the second pump and the probe, let's say. And then you can Fourier transform with respect to those 2 timescales. And so if you Fourier transform with respect to those 2 timescales, then you'll get a response function which is a function of 2 frequencies, the frequency conjugate to the wait time and the frequency conjugate to the second wait time. Yeah? And then you can plot the response functions in the 2-dimensional frequency plane. Remember, these 2 frequencies are the 2 frequencies conjugate to the 2 wait times. And you can look at the structure. And as Peter just explained, you have this wonderful feature that that stuff like multi-particle continua or inhomogeneous broadening, they broaden your signal in specific directions in the 2-dimensional frequency plane. But if you measure the width in the transverse direction, that tells you something about the intrinsic sort of spectral width. And so you can use that sort of transverse direction width of the signal to learn something about intrinsic relaxation rates of the sharp excitation modes that maybe underlie a multi-particle continuum or which are being smeared out by inhomogeneous broadening in linear response. And you can read out both T1 and T2 times, where T1 is sort of the dephasing time of a particular mode, and T2, other way around. T1 is the energy relaxation time of a particular mode, and T2 is the dephasing time. Okay. So the first application, which Peter also briefly mentioned, is phosphorus doped silicon. So of course, phosphorus doped silicon is a very old experimental system. And the first experiments were done almost a century ago. It was the original motivation for Anderson localization, also for Ravindra Bhatt and Patrick Lee's work on random singlet phases. And a lot of work has been done on phosphorus doped silicon. So what new thing could there possibly be to say about phosphorus doped silicon in the 21st century? Yeah? But even though a lot of work has been done on phosphorus doped silicon, there are still open questions. And one reason is that, hey, let's work in the insulating regime of phosphorus doped silicon. Yeah? Now, the usual lore says that the insulating regime of phosphorus doped silicon is an Anderson insulator of sorts, but not so fast, because phosphorus doped silicon is an electronic system. Electrons have Coulomb interactions, for better or for worse. And how do the long-range Coulomb interactions actually modify the sort of Anderson insulating behavior of the insulating phase of phosphorus doped silicon? Theoretically, to my mind, this was never completely settled. Yeah? There's an old idea from Anderson that maybe it's sort of somehow smoothly connected to an Anderson insulator, but is this idea really correct or not? And in the past, this couldn't really be cleanly settled experimentally because of inhomogeneous broadening. So in the insulating phase, the elementary low energy excitations are Mott dipoles, little short range resonances between electrons sitting on this side and sitting on that side. but you have Mott dipoles at all frequencies. And so you do any sort of global sort of linear response probe, and you just see some broad fuzzy structure because of inhomogeneous broadening by disorder. You can't actually resolve individual Mott dipoles in linear response. With 2D coherent spectroscopy, you can. So the idea is to use, is to probe relaxation rates of the Mott dipoles in the insulating phase of phosphorus doped silicon using 2D coherent spectroscopy. And at this point, I really want to emphasize that the relaxation rates of the Mott dipoles are not the same thing as AC conductivity. Yeah? So we will be asking, you have a Mott dipole at frequency omega, how does its relaxation rate depend on omega? This is not the same thing as AC conductivity. And as a simple way of illustrating this, let me just observe that if you really had a non-interacting Anderson insulator, then the relaxation rate of the Mott dipoles would be 0, but the AC conductivity would be omega squared. And these two things are not the same. So relaxation rates of the Mott dipoles are conceptually distinct to the AC conductivity. And they're not something that had really been worked out before. So they can be measured with 2D coherent spectroscopy. They were measured in this paper of ours from a few years ago. I'll just give you some of these sort of stylized facts. So you can measure the intrinsic relaxation rates of the Mott dipoles. The intrinsic so here you can change the doping, and starting in the insulating phase, as you get closer to the metal, the signal actually sharpens. So the relaxation rates go down as you get closer to the metallic phase, which is maybe backwards from what you would naively have expected. You can look at the frequency dependence. The frequency dependence of the relaxation rate is linear in frequency, both T1 and T2 relaxation rates. You can also look at the temperature dependence. So the experiment can be done at 5 Kelvin and 25 Kelvin. And the surprising feature here is that the signal is sharper at 25 Kelvin than at 5 Kelvin. So it seems that the relaxation rates of Mott dipoles are actually lower at higher temperature, which again is maybe backwards from what you would naively have expected. So what's going on? Well, in principle, I could have spent my whole talk on this, but I'll just give you sort of highlights. So the basic, at least what we think is going on is there's two pieces to the puzzle. The first piece is that the density of states of the Mott dipoles is being reconstructed by the Shklovsky-F-Roche mechanism. So that's step one. First, you have reconstruction of the density of states of Mott dipoles by the Shklovsky-F-Roche mechanism. And then you have long-range coherent hopping of the dipoles mediated by the long-range Coulomb interaction. And that can be treated through Levitov's real space renormalization group. And you take these two ideas and you marry them together, and you get relaxation rates which are linear in frequency with log corrections, consistent with what is observed in experiment. And moreover, because we're relying on long-range coherent hopping, it's quite plausible to say that, look, increasing temperature spoils coherence, it spoils long-range coherent hopping, so maybe it suppresses the relaxation rates. So, yes, Piers. Yes. So there's two pieces to the puzzle. The first piece to the puzzle is that the density of states of the Mott dipoles is non-vanishing as you take frequency to 0. Yeah? That's what Shklovsky-F-Roche is doing for you. The second piece to the puzzle is that dipole-dipole interactions are 1 over r cubed. Yeah? So if you are looking for another dipole within a frequency window of size omega, you have to search over a space that's of volume 1 over omega, yeah? Which means you have to search over a space with radius 1 over cube root of omega. And the matrix element, if you take 1 over cube root of omega and you plug that into the dipole matrix element, that gives you a matrix element which is linear omega. So you have coherent hopping with a matrix element linear omega, and that gives you a relaxation rate which is linear omega. Yes, correct. Yeah. And the logs come from doing things carefully and actually taking these words into account. But if you don't care about the logs, you can get the linear omega just from that basic scaling argument. Okay, so we think this explains the experiment. I will caution that the derivation makes assumptions which are definitely not true. So for instance, it assumes the dipoles it assumes multipole expansion, and it assumes that the frequencies are low compared to the characteristic energy scales, and neither assumption is really valid in the experiment, but it seems to work. Good theory sort of often ends up working even beyond its regime where it's well controlled. One other caveat I'll make is that usually when we do, let's say, Fermi liquid theory, what one usually calculates is the lifetime of an injected electron. What we're calculating here is something different. We're calculating the lifetime of a Mott dipole. But that's okay, because the dipoles are the quantities that are naturally coupled to in the experiment. They're the low energy excitations of the insulating phase. So I think it's the right thing to be calculating a lifetime for, and they're marginally well defined. So that's why we call this the marginal Fermi glass. You can also sort of motivated by this, you can define a more abstract problem, which is just relaxation rates of interacting dipoles. So dipoles with 1/r³ dipole-dipole interactions, they show up in phosphorus doped silicon, but they also show up in all sorts of other contexts: polar molecules, quantum magnets, NV centers, phonons in polar crystals, and so forth. And so we could ask about their relaxation rates as a function of frequency and temperature more broadly. And in this paper here, we developed a scaling theory for the relaxation of interacting dipoles. And it turns out the scaling theory only depends on a handful of parameters. So it depends on the low energy density of states of the dipoles. It depends on the dimensionality, and it depends on the temperature, in particular, whether the temperature is 0 or non-zero. And then you get a set of universal scaling results, which are summarized in these two tables. Yeah. So at 0 temperature, in 2 dimensions, the relaxation rates are 0. In 3 dimensions, if the low energy density of states is constant, then the relaxation is linear omega up to logs. If the low energy density of states vanishes, then the relaxation rate actually has an essential singularity as a function of frequency. At non-zero temperature, the relaxation rates are always power law functions of temperature. In 3 dimensions, it's just a single power law. In 2 dimensions, T1 and T2 actually scale with different powers. So there's this parametric separation between T1 and T2, which comes about as a result of spectral diffusion. Okay. So we've worked out a scaling theory for interacting dipoles in great generality. Yeah, and this is, again, the sort of thing that one could probe with 2DCS, has been probed for the electron glass, but could also be probed for strongly interacting dipoles in a broader set of contexts. What else? Well, something else that one could do is, remember I said the thing that 2DCS is good for is if you have sharp excitations, but they're obscured in linear response, then you can resolve them with 2DCS. Another context where you have sharp excitations and they're obscured in linear response is spin liquid phases, or more generally fracton phases. So these are exotic phases beyond the Landau paradigm. And now they have the property that local probes create elementary excitations, the spin-ons, let's say, in multiplets. Yeah? And because local probes create excitations in multiplets, keep going. Yeah. Because local probes create excitations in multiplets, now what linear response sees is a multi-particle continuum, and you cannot resolve the sharp underlying excitations. This is a problem that you could solve with 2D coherent spectroscopy. So for example, you could consider doing 2D coherent spectroscopy on various paradigmatic models of either spin liquids or fracton phases. So in this paper, we considered the toric code phase as the paradigmatic example of a spin liquid, and the X cube and Haar code phases as examples of fractons. And you look at their response in 2DCS, and you conclude, essentially, again, skipping details, that there are distinctive signatures of each of the following. There's distinctive signatures of deconfined quasiparticles, of whether those deconfined quasiparticles can further fractionalize, and of whether any of the elementary excitations are immobile, as would be the case in fracton phases. And in conjunction with linear response, this provides a nice, clean, purely spectroscopic diagnostic for spin liquids, both conventional spin liquids and fracton spin liquids. More work has been done on that since. So in this paper here, we pointed out that you could use 2DCS not only to resolve the existence of sharp spin-ons underlying the multiparticle continuum, but even to read off the spin-on self-energies. So you could do that by sort of measuring the intrinsic lifetimes as a function of frequency, and this tells you about spin-on self-energies. Then there were some very nice papers, first from Sid and then from Nandini, explaining how you could use 2DCS with crossed polarizations to detect non-trivial braiding statistics. So if you have fractionalized excitations with braiding statistics which are not just fermions or bosons, then you can detect that with 2DCS. You cannot tell what the braiding statistics are, but you can tell that they're non-trivial, that they're not just bosons or fermions. You can also detect braiding statistics in fracton phases. That's something we're currently in the process of writing up. So there's a lot of information that you can extract about fractionalized systems using this technique. And the hope is, I think, that this technique could do for fractionalized systems what something like ARPES did for band structures, and allow you to really spectroscopically read off a whole bunch of information that was simply not accessible through traditional experiments. Part 2 of the talk, 2DCS can provide unambiguous signatures of exotic states of matter, such as gapped spin liquids and gapped fracton phases. It can allow us to measure spin-on self-energies. It can even diagnose the existence of non-trivial braiding statistics. And so really, I would say it's the tool par excellence for characterization of fractionalized phases. And sort of characterization has, for a long time, been the great open challenge. We're pretty sure that fractionalized phases can exist, but how do you positively identify them and characterize them in experiment? Behold, here there is a set of techniques that can do just that for you. It can give you positive signatures of fractionalization and a way to characterize fractionalized phases. Okay, part 3. Now I'd like to talk about nonlinear spectroscopy of superconductors. So now the basic idea is to consider probing collective modes in superconductors. Again, Peter talked a little bit about this. I'll give you a slightly different perspective. So for now, the results that we have, I should say, are limited to clean superconductors. I think disordered superconductors would be very much richer. There would be a lot more to study. That's work in progress. I don't have results on that to share with you yet. What we've done thus far is clean superconductors, BCS superconductors, really just using the Anderson pseudospin formalism. So what we do is you have a BCS superconductor represented by Anderson pseudospins, and then sort of treat optical experiments by solving equations of motion of the Anderson pseudospins in the presence of light, and look at nonlinear response of superconductors in the Anderson pseudospin formalism to optical interrogation. 2 quantities in particular that we looked at. The first was gap dynamics following a pulse. So you sort of whack the system with an optical pulse, and then you look at the gap function delta as a function of t, and then also the nonlinear current, aka the third harmonic generation. And the quantities of interest for us here were both the Higgs mode decay rate, the quasiparticle redistribution rate, and the quasiparticle dephasing rate. Now, if you have a pure BCS superconductor, then the quasiparticle redistribution rate is 0, and the quasiparticle dephasing rate is also 0. So in order to make things interesting, we want to have a non-zero quasiparticle redistribution rate and dephasing rate. Ideally, maybe we would introduce nonlinearities beyond BCS, but that's too complicated. Instead, what we did is we just introduced these decay rates phenomenologically. So in the Anderson pseudospin picture, just by hand, you can introduce relaxation rates which correspond to quasiparticle redistribution and dephasing. And in principle, you can allow these relaxation rates to be non-trivial functions of energy, and see what this does. You do this. can analyze both S-wave and D-wave superconductors, allowing for energy-dependent relaxation rates. It's also very natural to consider interrogating the system by shining polarized light, yeah? And you could vary the light polarization and make that a probe, make that a tuning knob. If it's an S-wave superconductor, it doesn't matter so much, but if it's a D-wave superconductor, that's quite powerful because you can selectively excite different irreps by sort of changing the angle of polarization of the light. And we sort of clarified what combinations of the intrinsic relaxation rates can be extracted from the time dynamics of the gap function and from the nonlinear current. Turns out in S-wave superconductors, the signal is dominated by quasiparticles at the Fermi surface. In D-wave superconductors, we can access relaxation rates at both the nodes and the antinodes by varying the polarization. And yeah, polarization control provides a particularly useful knob for D-wave superconductors precisely because there are sort of different non-trivial irreps which you can excite by changing the polarization angle of light. So, conclusion of this part is that now we can extract a little bit of new information about clean superconductors by looking at nonlinear response and by allowing us to look at nonlinear response to light polarized along different axes. Dirty superconductors are likely to be very much richer, so that I'm pretty excited about, but sort of that's still in progress, so I don't have results to share on that yet. Okay. What have I told you? Firstly, looking at ultrafast quantum dynamics can provide a powerful new set of insights into quantum materials. It can be used to settle long-standing open problems in well-studied materials. In fact, even maximally well-studied materials like phosphor-doped silicon. It can be used to look for novel phases. It can be used to characterize phases which are hard to characterize with traditional experiments, like spin liquids or like fractons. It can be used to extract information inaccessible to conventional probes. And also, it's a good motivation for doing non-equilibrium in the solid state. Yeah? And for taking this entire body of work which has been developed on non-equilibrium many-body physics and actually applying that to honest-to-goodness material systems instead of just always cold atoms and synthetic systems. What more can we do? So in the last part of the talk, I'd just like to take maybe 5 minutes to survey what I see as some key open directions and possibilities for the field. Oh, come on. What? Okay. So the first thing, I said right at the beginning that the killer application for 2D coherent spectroscopy is that suppose you had sharp underlying excitations and they were obscured by the existence of a multiparticle continuum or inhomogeneous broadening or something else. Yeah? What if we didn't have sharp underlying excitations in the first place? There's no guarantee that we have to have sharp underlying excitations, especially if we're talking some strongly correlated system. If we did not have any sharp underlying excitations, are there still new insights to be gained from nonlinear spectroscopy? I mean, maybe it won't just be blindly applying the same ideas we applied before. It would require new ideas. Yeah? But it would be interesting if there were. Something else we could ask is, look, there's a bunch of different nonlinear spectroscopic techniques that we talked about. I spent the most time talking about 2D coherent spectroscopy, but there's various pump probe techniques, sort of nonlinear response techniques that I talked about in the last part. Are they all sui generis, or is there some broader unifying paradigm which allows us to think about nonlinear spectroscopy as sort of one thing instead of a collection of different tricks? Is there a general understanding of how to go from here's some physics we want to see to here's the nonlinear spectroscopy experiment that can probe it? Yeah? Right now, it's a bit of an art form. There's a lot of reliance on serendipity, coming up with some clever nonlinear response experiment that sort of can see interesting physics. Is there a way to turn it from an art into a science where you can systematically say, okay, here's the physics I want to probe, and voila, this is the experiment that needs to be done in order to probe it? And finally, I would say that, look, at least from a theorist's point of view, all the theoretical work on nonlinear spectroscopy has been close to some weakly interacting fixed point. Now, I'm not saying that it's necessarily a free electron fixed point. So in the context of spin liquids, you could work close to the toric code fixed point or close to the x cube fixed point. Now, these are strongly correlated phases, but you're close to some fixed point where in the proximity to that fixed point, you have some effective description in terms of some weakly interacting quasi-particle degrees of freedom. That's the usual theorist crutch. You find some solvable point, some weakly interacting quasi-particle description about that solvable point, and then in terms of those weakly interacting quasi-particles, you can formulate a description of nonlinear spectroscopy. Can we do it without that crutch? Now, can we meaningfully talk about and analyze nonlinear spectroscopy in contexts where we don't have a weakly interacting quasi-particle description, or in a context where we're not near equilibrium? So actually, even though I started off by talking big game about out of equilibrium, all of the experiments or sort of proposed experiments I was talking about were near equilibrium. Yeah? They were starting with you have some equilibrium phase of matter, and then you perturb it and you look at the nonlinear response. But what if we were very far from equilibrium? Is there interesting nonlinear response to be done to characterize far from equilibrium solid state systems? Yeah? So I think that, again, would be an extremely interesting question on which we don't have very much to say yet, but I think it would be a good question for the future. So I think this is a very interesting new frontier, both for many-body non-equilibrium theory and for materials physics and for sort of experimental nonlinear optics. Now, what we really need is universal perspectives, which are not specific to any one material or model. 2D coherent spectroscopy is, I think, one such potential paradigm, but we need more. And we want paradigms which are not limited to weakly interacting or near equilibrium systems. I think there's a lot to be done here. There's stuff for analytic theorists like me to do. There's stuff for computational physicists to do, stuff for experimentalists to do. And I really think that there's a lot to be learned from sort of everything we've developed in many-body dynamics and actually porting that over and applying it to the solid state context. Okay, with that, I'll just thank the various people with whom I've had the pleasure of collaborating on this topic. First and foremost, Peter, who gave the previous talk. So Fahad, Dipanjan, Sarang, Wonjun Choi, Yongbek Kim, Oliver Hart, and my new student, Wei-En Seng. And with that, I will conclude, and I'm happy to take questions.
One question about the superconducting part that you were doing with the gap dynamics. So are you just assuming that overall couplings that give rise to superconductivity are fixed? Because normally if you are creating non-equilibrium distributions, that can also change the effective coupling.
Yeah.
So is it?
Yeah, so we're assuming, yes, we are assuming the couplings giving rise to superconductivity are fixed. Okay. And it's just straight equations of motion for BCS for Anderson pseudospins in the pseudomagnetic field with phenomenologically introduced damping. That's it.
And is there a separation of timescales in some cases where this would make a clean case? Because is it clear that?
I suppose it would be, what we really want is that the pump is not so strong as to very strongly modify the underlying interactions. So this is coming back to the idea of where we're mostly looking in sort of near equilibrium settings. It would be wonderful to be able to say something in full generality, but we just don't have the ability to do that yet.
Okay, thank you.
Talk. The experiments that Peter told us about were mainly Chi3, if I remember right,
yes,
responses, meaning most generally a response of quantity A to force terms B and C.
Yep.
My question to you is, can that be done with equilibrium, imaginary time, Green's functions? Is there a generalized fluctuation dissipation theorem that enables me to completely bypass the use of ugly Keldysh-Green's functions, or do I have to use them?
Yeah, so here, everything that we're doing is near equilibrium. So yes, you can even calculate it just with straight Kubo formula.
So 1, 2, 3 Kubo formula.
Yes. Yeah.
Okay.
So yes, these nonlinear responses are computable within just regular Kubo formula. No.
So it's really equilibrium response.
Yes.
The word non-equilibrium should be saved for more drastic response functions.
It's near equilibrium response, but I think the answer to your question,
if I take a magnetic field and I look at the response, the chi cube response to the magnetic field, I do not call that non-equilibrium, right? Even if I do it at a finite frequency.
Yeah. The chi3 responses.
I should not call this a non-equilibrium.
Well, I think the last part, when I was talking of sort of gap function dynamics and quasi-particle relaxations, that I would not call equilibrium in that sense. But the chi3 responses, yes. Those essentially are sort of nonlinear but equilibrium response functions.
Okay, very good.
I guess one way to say it is that you know, in the pump probe, you have a ground state, you pump it to an excited state, and then in that state, you do a linear response, and then come back.
Yeah.
But you are doing it in a pumped state, and that pumped state could be out of equilibrium, far out of equilibrium.
But Piers, what I would say though is that yes, it's true you can compute everything purely on the basis of sort of equilibrium correlation functions. But if in terms of understanding what's going on, it's very useful to think of the dynamics of the excitations which you've created. And that's true for all the examples I gave, where you can really think about you've created some excitations and then they're time evolving in some way and then you're relaxing back to the ground state. And like thinking about the dynamics of those excitations gives you a very clean understanding of the nonlinear response functions, even though, yes, you could compute them purely on the basis of equilibrium correlation functions.
More questions? Just a minute. There was Ravindra here. Go ahead.
My question is regarding the gap dynamics, delta T.
Yeah.
You see in the BCS superconductors, there is a well-known effect known as phonon bottleneck. So what happens that, so once you excite this, destroy the superconducting condensate, your quasiparticles, they relax by recombining. So the K up combines with minus K down to become a Cooper pair, goes down in the condensate, and it ejects a phonon. Now the thing is that if the phonon diffusion is slow, the system is not, the diffusion of the phonons is not happening at a fast rate. The phonons stay there and the phonon get reabsorbed and it breaks the Cooper pair. So your relaxation to the condensate is slowed down due to this phonon bottleneck. So is this phonon bottleneck acts in the nonlinear response? Have you
so like I said, we don't put in any microscopic relaxation. The relaxation is introduced purely phenomenologically. Right? But this phonon bottleneck would presumably manifest as some non-trivial frequency dependence of the relaxation rate, right? So we do in fact consider frequency dependent relaxation rate. Now, do you know what the frequency dependence you get from phonon bottleneck is? Okay. Right. So I think the main thing that matters is whether the relaxation rate vanishes at the Fermi surface or not. And you get different behavior if the relaxation rate vanishes at the Fermi surface. So all you can tell in the nonlinear response is whether the relaxation rate vanishes at the Fermi surface or not. Now, if it is the case that phonon bottleneck causes the relaxation rate to vanish at the Fermi surface, which seems plausible to me, then yes, that one would be able to tell in nonlinear response. You couldn't tell whether it was because of phonon bottleneck or something else, but you could tell, aha, like intrinsic relaxation rates vanish at the Fermi surface or don't vanish at the Fermi surface.
Just to go back to, I think, Piers, you had the question on whether you can just do this by Kubo. I think it's strictly speaking correct, but if you structurally, there's one extra challenge. So what you normally do by fluctuation dissipation is response as some nested commutator. Fluctuation dissipation takes that and makes it into a correlation function. But in nonlinear response, it's actually several commutators. You can get rid of the last one. So that's fine if you're doing a pencil and paper calculation, you can deal with that. But if you ever want to sample anything numerically, you have a horrible sampling problem because you need to you need to very accurately get the two numbers and take their difference. So that doesn't matter for linear response. You can often just analytically continue, but now you have the extra hassle of the error bars on analytically continuing something will now also get magnified because you have to subtract two numbers to get a response. So just to say it's not, if you think of anything you have to do numerically, then it's not quite as easy as doing linear response. It becomes complicated for that sort of stupid reason, but it's real.
You have Mike.
That the problem with the constant density of states and a 1 over R cubed interaction is the same problem one would get with tunneling two-level systems in just glasses.
Essentially, yes.
So there also one would expect the two-level systems to have sort of omega linear relaxation rate. Did people measure that in NMR?
I would say it depends on what the low energy density of states of the system is.
It's constant, right? Same as the spectroscopy.
Okay, so in that case, I think, yes, I would expect linear omega. That's non-universal though, yeah. Yeah, but the scaling theory, I mean, doesn't say anything about what the coefficient is or should be.
This Mexican hat picture, this is really a question for Peter. The Mexican hat picture that you presented, the amplitude and the phase modes, I mean, that's a long-standing prediction of CS. It was not verified experimentally for a very long time until I heard about it for the first time in the context of MGP2, where I believe it's a multiband superconductor. And I want some clarification. So it's a different effect compared to what you are measuring in NBN. And you're doing it with a nonlinear optical method, whereas that was done with a straight. Is that right? The question is, so, well, first of all, it's a compliment that is this the first time that the amplitude mode has been observed at all in a conventional superconductor? That's question one. And I did hear about this amplitude mode in a different context, that is with MGB2, and which you didn't refer to in your talk. So how is that different, that work different from what you're doing is one question.
Spectroscopically, observation of the amplitude mode was first done in Raman by Klein.
By Raman, okay.
And then explained by Littlewood and Varma and Littlewood. And that's in a very particular case of niobium diselenide, where there's a charge density wave that basically allows you to couple to the amplitude mode. So that's a very specific case. To see it generically, then you have to couple nonlinear. And so these experiments were first done with nonlinear terahertz done by Shimano at the University of Tokyo. The papers, there's a series of papers with the first author, Matsunaga. The way they did it was, I think they had the right general idea of what was going on, but when you do the experiments in 2D, this two-dimensional scheme, in particular, there's some other technical aspects of it. It's kind of a more straightforward probe of the physics. We did it in niobium nitride, which is single band. We also have a paper that came out earlier this year in MGB2. And there, potentially the structure, the collective mode structure is much richer because it's multiband, as you said. In principle, it's richer. We actually didn't see that. And so my former postdoc, who I did these experiments with me, this is what he's working on now in his own independent position, is trying to change the experiments around to possibly see some of these other collective modes, things like the Leggett mode, these multi-band collective effects.
Okay, the other comment I had is in superfluid helium-3, these collective modes are well known. And between the A phase and the B phase, and in fact, in the B phase in particular, they are instrumental in pinning down the fact that it is a beat. Whereas in the A phase, because they appear as extremely sharp resonances that couple sound, whereas in the A phase, these features are broadened out due to pair breaking effects and so on. So it's less convenient to observe them. The lesson from that, I think, is that, well, it would be nice if these new techniques you're proposing could somehow pick out these order parameter collective modes, which presumably are richer in these D wave states and so on. So I hear a lot of debates about whether it's D wave or X squared minus Y squared or D plus S, et cetera, et cetera. And if one can come up with a technique where you could see these collective modes, probably you will have a better chance of answering those questions.
I think in general, if you could use probing of the collective modes as a diagnostic for what the character of the order parameter is, that's great. Our observation is that there's enough low energy stuff around in nodal superconductors that tend to damp out these collective modes, and so they're hard to see. So it's the same thing that you referred to. I don't think we do much better, but maybe there's a way we can be clever. We just haven't been clever yet.
Okay, last question from Ravin.
Short questions to you, Rahul. The first thing is you mentioned that it was good for gap spin liquids. What about spin liquids without gaps? And the second thing is you said it was much more interesting in disordered superconductors. What makes you think that?
More interesting for gap spin liquids purely because gap spin liquids are harder to characterize with conventional techniques. So if you have gapless spin liquids, let's say Dirac spin liquids or something, then they would have linear response signatures like pinch points and neutron scattering. And so then you could hypothetically just do a linear response neutron scattering experiment and look for pinch points. Like, why bother doing anything nonlinear? The reason I was specializing to gap spin liquids is just because in gap spin liquids, as far as I know, there's nothing in linear response. And so nonlinear response is the only game in town. But yeah, you absolutely could do analogous experiments for gapless systems as well. It's just there doesn't seem to be as much point because there's things you could already do in linear response. Now, as for why dirty superconductors are interesting, well, again, different people could have different motivations, but for me, I'm very interested in localized superconductors, and I'm sort of very interested in understanding, having ways to probe, let's say, energy transport in localized superconductors and probing energy relaxation in localized superconductors, which is something that I think should be possible to do with nonlinear response techniques. So at least that's the question that I'm interested in. Somebody else could be interested in something different.
I want to add one thing there. So, this Higgs mode is very close to the 2 delta pair breaking energy scale in a BCS superconductor, a clean superconductor. But if you put disorder, even in a BCS superconductor, the gap scale remains unchanged and the Higgs mode moves down in energy. So there's a separation between these two. So you should be able to see the Higgs mode more cleanly. And that would be, I think, useful. 1 second.
Just had a question. I mean, why not a disordered normal material? I mean, I thought that there are universal conductance fluctuations, and the AC counterpart of that will be addressable by non.
Yeah. I think that would also be interesting to look at, but infinite number of problems in finite amount of time.
Okay, I think we've had a great discussion. Let's thank both the speakers of this very exciting session, and let's also continue the discussions in the coffee break. And then after that, there's a